All right, let's jump right in. Think about this for a second. You're out in the yard watering the plants with a hose. You put your thumb over the end, and what happens? The water speeds way up, right? It shoots out in this powerful stream. Now, common sense tells you that the pressure must have gone through the roof. But did it? This is the big question we're going to tackle. It seems so straightforward, but the answer is actually one of the coolest and most counterintuitive ideas in all of physics. So what's your gut feeling? Faster water means more pressure? Well, hey, if you said yes, you're not alone. That's what most of us would think. But it also means you're falling for a really common misconception. So let's unpack the surprising truth about how a fluid's speed and its pressure are actually connected. I mean, it just feels right, doesn't it? Anything moving faster feels more forceful. So our brains just automatically connect that speed with higher pressure. But as we're about to find out, when we talk about the internal pressure inside the fluid itself, physics completely flips our intuition upside down. Okay, so to crack this puzzle, we have to change our thinking a little bit. We need to stop thinking about force and start thinking about energy. You see, a flowing fluid is really just a system of energy. And just like any other closed system, that energy has to be conserved. It can change from one form to another, but the total amount of energy has to stay the same. And that brings us to the hero of our story, Bernoulli's principle. Now, don't worry about any complicated formulas just yet. At its heart, this principle is simply about the conservation of energy. All it says is that for a fluid flowing along, its total energy is constant. So, what kind of energy are we talking about? The first piece of the puzzle is something called static pressure. This is the pressure the fluid pushes out with in all directions on the walls of the pipe. You can kind of think of it as the fluid's potential energy, just waiting there pushing outwards. And the second piece is dynamic pressure. Now this is the really interesting one. See that V in the equation? That stands for velocity. So this type of pressure is directly tied to the fluid's speed. The faster the fluid is moving, the more dynamic pressure or energy of motion it has. Simple as that. So here's the absolute key. If the total energy has to stay constant, and you've got these two types of energy, the static, pushy-outy kind and the dynamic, motion kind, they have to be in a constant trade-off. We'll assume the pipe is level, so the height part doesn't change. That means if one type of pressure goes up, the other one absolutely must come down to keep the whole thing in balance. And boom, here it is, the big reveal from the source material. It's an inverse relationship. When the velocity goes up, that dynamic pressure goes up, which means the static pressure has to go down to conserve the total energy. So faster flow actually means lower internal pressure. Wild, right? I know. This can feel a little abstract just talking about it. So let's look at a visual that shows exactly how this plays out inside a pipe. Honestly, once you see this, the whole concept just clicks. Okay, check this out. On the left, in that wide section of the pipe, the fluid is just moving along, kind of slow. That means it has low dynamic pressure, and because of the trade-off, it has high static pressure. You can literally see it. That higher pressure is able to push the water in that little vertical tube way up to that height, H1. But now, look what happens when the pipe gets narrow. The same amount of water is forced through a smaller space, so it has no choice but to speed up. Its velocity, and therefore its dynamic pressure, goes way up. So what has to happen to keep the energy balanced? The static pressure must drop, and that's exactly what we see. That lower static pressure can now only push the water up to that much shorter height, H2. It's a perfect visual proof. Wide pipe, slow fluid, high pressure. Narrow pipe, fast fluid, low pressure. The complete opposite of what you'd probably guess. And this table just sums it all up perfectly. It's a clean, simple inverse relationship. As the area shrinks, the velocity ramps up and the pressure drops. That is the fundamental trade-off at the very heart of fluid dynamics. So, okay, this is a neat little physics trick. But why does it actually matter? Who cares? Well, it turns out that misunderstanding this very simple principle can have some seriously expensive and even destructive consequences in the real world. For engineers, getting this right is absolutely non-negotiable. It tells them how to size massive industrial pipes correctly. It dictates where you can and can't put valves in a system to avoid dangerous pressure drops. And maybe most importantly, it helps prevent something nasty called pump cavitation. That's where the pressure drops so low that bubbles actually form in the liquid, and then they collapse with so much force they can literally destroy metal parts. So yeah, this isn't just some question in a physics textbook. Understanding this trade-off is the difference between an efficient, safe fluid system that runs for years and one that could fail in a really catastrophic way. It's a true cornerstone of safe engineering. And that pretty much wraps it up. So the next time you see a river narrowing and speeding up, or even the next time you put your thumb over that garden hose, think about that invisible pressure drop that's making it all happen. Now that you know the secret, where else do you see this speed for pressure trade-off at play in the world around you?